Chaitanya, you there? So we are starting the next session about uh, process management, process management in kernel. Basically, we will be covering around the process management steps, some of the source code browsing, major concepts into that area, and that's quite really vast. Again, we will be covering the most of the part which you will be needing to you need to deal with the processes, threads, and everything while writing your drivers or writing your kernel modules. So uh, the most important concept starts uh, with the process. What is the process? So I will take you to a session where we'll try to understand what it is. So the process in this uh, particular session, we will try to cover the system structure, kernel architecture, Linux processes, process states, process relationships. Basically, this is very important concept in the Unix systems, Unix family systems, process queues, and there are some specific to process management things which we'll be looking at. So uh, Chetan, just for reviewing our work, I have given some exercises. Did you try doing it? Did you completed those exercises? Chetan, you there? Are you able to listen? So, did you complete your exercise? Okay. So, try doing that. There was Is there any difficulty you are facing in those exercise? Okay, okay, okay. It's all right. So keep those exercise. Do it at least once hands-on. It will be very good because debugging sessions are very critical. Uh, all the debugging hands-on is very important to basically dealing with the kernel later on. So you do it once you get the time for that. We'll be starting this session on process management. Today we will try to cover the basic concepts on the process management area of the kernel, and the basic concept of the process threads, and the architecture, and some of the source code browsing. So there will be now mostly your exercises will lie on uh, basically source code browsing and finding out what is the relevant and um, basically relevant structures, and knowing the conceptual understanding of the system architecture at kernel. So we will let's start it. uh, so the today's agenda is basically we are going to cover system structure, kernel architecture, Linux processes, the processes state, process relationships, process queues, and miscellaneous of that this area. So basically, what are the hacks around this area? So we will be looking at it. The system architecture, we have seen this picture a lot of times. uh, basically your user space is actually entering into the kernel mode by triggering a system call, uh, or generating any exception. So basically, this kernel interface is, this whole kernel modules are there is central kernel, which we call it as a base kernel. The base kernel manages the processes, it schedules it to the CPU, it manages the signals, it manages the memory. So this is the base kernel. We call it basically the base OS kernel. And it consists of process management, virtual memory, uh, and basically these two. So you can say the managing the computation means CPU, and managing the memory is the base kernel, and managing the storage is the file system and device driver, the disk driver. Other peripherals, you can see if there is HPA card into it, you need to have separate kind of device driver for that. You have network cards, you need separate kind of device driver to that. So this particular picture says that the central kernel is actually dealing with all and managing all those modules around the kernel. And everyone talks to this particular area of the kernel, and gets the information, and basically do the and serve the application. So this is the core part of kernel. And here uh, so basically if I want to divide this process management part, basically I would say there could be, you can divide it into two parts. The bottom layer is basically the scheduler, which actually manages the run queue, execute the process over CPU. Also it manages um, it also manages the priority of the processes, scheduling it, putting it into the run queue. And also this part of source code is mostly platform dependent. So it would be like, if you have x86 kernel, that a lot of code has been written into the assembly language in simulator, in scheduler. So if we open any of the um, so I will open source code of scheduler, and we will try to see what are the source code actually written in assembly. So okay. Okay, so inside directory called kernel, you could be able to see uh, a lot of files which is related to process management. You can see fork here, you can see kexec also here. It's a part of base kernel. You can see the credentials, you can see the CPU set, you can see config.c, You can see all the audit calls there. You can see the C group. Okay, C group feature is a component, uh, is the subsystem of C group. uh, you have some memory related files also. You can see here pid.c. So these all are the files which is mostly concerned to managing the CPU and memory for the system, and go into the scheduler. Yeah, so scheduler, you can you must read this some amount of source code here also. uh, like this particular have CPU priority. See, look at the algo and the comment on that. This code tracks the priority of each CPU so that global migration decisions are easy to calculate. Each CPU can be in a state of as follows: invalid, idle, normal, RT1 and RT99. So RT1 1999 is something like what is the consumption of CPU. So if it is 1%, RT1, and so on. So RT99 for 99%. Normal is like it is that state I don't know. Invalid is something when CPU is faulty or something like that. Idle is for CPU is not doing anything. So going from the lowest priority to the highest priority, CPU in the invalid states are not eligible for routing. The system maintains this state with a two-dimensional bitmap. So what you can do, you can have a look into the code here. You read the comments very carefully. There are a lot of information about it. If you don't get some of the things out here, you must ask, right? So we will try to catch up something. I've just taken you here to show that related information and source code. You can find it here. Now let's try to catch one corner of it so that you can start understanding the system. So okay, so this is another kernel architecture picture which can tell you how actually kernel manages lot of things to serve applications. So you can see the same modules. There is network system. Okay, that network protocol module underlying with network card driver. Then file system will have underlying device, disk device drivers. Memory management is your RAM, how the virtual memory is managed in your RAM. And process management is having underlying scheduler. So scheduler is actually part of process management. And so process management and inter-process communication, so these three are quietly clubbed: memory management, process management, and inter-process communication. And this is the core kernel which actually manages most of things for your process to execute, scheduling threads, managing memory, uh, and basically facilitate any of the threads or process to run into the system. So looking at that architecture, um what are the conditions? Basically we have to understand what are the conditions when a process enter into the kernel mode. So can you explain, Chetan, can you explain what these three conditions you are seeing at your screen? Chetan, you there? Chetan, you there?
Hello, yeah,
Yeah, Chetan, can you are you able to see the screen properly?
yes, yes.
Yeah, yeah. So basically, I was telling about in what conditions basically process enters into the kernel mode. Can you explain me these three conditions? These are the possible conditions when process enters into the kernel mode.
Yeah, means one is that whenever a user try to execute any system call, read, write,
Right.
any any socket related, send, receive anything.
Yeah.
So then the interrupt will be raised to, and so that the contest will move to the kernel, like it is on behalf of user process request.
Mm-hmm.
Yeah, yeah. Like second one also, it's by timer. Um, Second condition, like Demons normally has a notion like whenever a timer expires, it will ask to call a specific handler.
Right.
Mm,
Right.
yeah, but my question is how in that case like like kernel triggers that function handler, but how, but it won't go to kernel mode, right?
Not exactly process gone into the kernel mode, but basically the CPU state gone into the kernel mode. So that let's say a page fault happens, something happens, but your context will have to move into the kernel mode so that they can serve the process. So process usually go into the another state, but at some point in time it has to execute in kernel mode, right?
Mm, mm.
Yeah, so your thread context has to tell that this is the page fault, so your thread context for some time comes into the kernel mode.
Okay.
Yeah.
And third one is like it's like exception, like we may call as like a synchronized interrupt.
Right.
So so what in the exception condition, kernel will take necessary action to clean up or recover depending on the condition.
Yeah, basically it crashes most of the time. Like segmentation fault is also a virtual memory exception, right? So that actually triggers the kill of the process. So
Yeah,
these are all the three conditions. Okay, for any point of view, for your knowledge point of view and your interview point of view, these three conditions are very critical because everybody asks these questions, and I will also tell one more thing you to do. um, I will, okay, once we'll cover the task structure, I'll give that assignment to you guys. So let me let me open a window here. I will assignment. So So whatever the exercises I am giving you guys is one of the very critical one, uh, because I would say if you practice on those exercise, if you put your efforts into that, these are the basic knowledge of the kernel, which everyone expects for a kernel engineer to have. So this without this you won't be able to do anything in kernel, because kernel is quite vast field, very vast source code base. The thing is, you need to know the architecture very well, and you need to know the ways of doing things inside kernel. So that is making it more complex usually most of the time. And Chaitanya, today's session will only last for 2 hours. We have theoretical. This is going to be mostly theoretical session, so we are not stretching it for longer period. Okay, because hands on thing is quite interesting. People can take it for longer time, but maybe a bit of uh, conceptual and theoretical, we should not stretch it more than 2 hours. So this is what we are refining some of the training tactics in our practices also. So anyways, we are trying to help in a way how good we can give to the people. So we okay, so these three are the conditions when any process running on the user space uh, enters into the kernel mode. And okay, so yeah, this is actually this is actually your process address space thing. User mode is stack. Basically what was written in the process, where is that? Okay, I don't have that picture for the uh, for showing you the process address. Let me search it for you. Right, so look at this is quite very interesting, and I would say one of the most conceptual understanding to any of the process. Looking at any process, you must be hearing it from long time that 64-bit the 64-bit processors has bigger memory. So basically, what do you mean by any bit of the process? Something like 32-bit process and 64-bit process or 16-bit process. What do you mean by that?
So it is the like a number of bits a processor CPU can process at a time.
Right. So this is
Something
about
like a data bus bit.
right. So that is correct. I mean, let's say I have a processor which can add two numbers of 64-bit, okay, in a one instruction set.
Yeah.
Right, let's say I have something on accumulator is actually that calculating part of ALU, your arithmetic logical unit on the processor. So 64-bit number is saved there, so adding another 64-bit number to it is just single instruction cycle, right? You just get into the ALU, and you will get the result of that. So processing power is not is scaled to double. Basically 32-bit processor could be able to deal with 32 bits only, but at the same time 64-bit processor can deal with the 64-bit. But what does it mean to have 32-bit process or 64-bit process?
Like you can fetch 32 bit at a time, right? One read it will fetch 32 bits of data.
Okay, so so I'll tell you one thing very very interesting in that. So when I say 16-bit process, that means once you compile that process, right, you will have a pointer size of 16 byte.
Okay, yeah,
Yeah. So there it starts. How much if the pointer is 16 bytes, that means it could able to address the locations 2 to the power 16, right?
yeah,
Which is 64k.
okay,
So 64k is your process address space,
yes,
right? So let's look at the architecture in a way. I'll open creately so that we can draw it, we can try and find out the concepts behind it. um, so uh, so when we say that it's a 32-bit process, that means its pointer is going to be 32-bit, right? and
yeah,
and once the pointer is 32-bit, that means it is capable of addressing 2 to the power 32 bit, 2 to the power 32 location, and that makes it nearly 4 GB. So 4 GB is the process address space of 32-bit process, right? So now we'll look at the examples here. uh, okay, let creately open. Till then we will look at this. So this is actually your process address space layout. So every address range in your process address space is defined. So where you keep the, whenever you actually compile any of your source code, you actually build two things. You you make a data section and bss section, and you make a text section which has the instruction sets. All right. So when you make this program running into the system, so if it is a 32-bit compiled binary, it will actually have the virtual address space mapping to the 4 GB space, but may not be used, or it actually basis on the it actually depends on the need basis. It may not reserve the whole virtual memory, right? 4 GB of virtual memory, but it will always have the mapping which is required by your process. So in your process address space, it starts from 0. You can see that. Oh, where is that? Okay, so you can see that this is 0, right, unused, and from here it is ffff, right, all the f. So it is 32 bit, 8 times f. Now looking at this whole, there is address, basically address range, where we have decided what to keep, where to keep code. You can see that read only code and data, right? Read and write data, which is your data segment. Okay, so it is actually loaded from your hello executable file. We will also able to see that this portion is actually your compiled binary. It is loaded from your compiled binary. Now there are a lot of things which is required for a process to run. Something like you have runtime shared libraries, right? There would be some memory map reasons. We'll cover it up later on. Will or you just have a check on this, what is memory mapped reason for any shared libraries. There are shared libraries, there are shared files which is memory mapped. So there are different.
memory mapped means address some memory.
What?
No, memory mapped means they given some memory, yeah, in the RAM.
Okay, just in case, I will say that there are set of processes which actually shared a memory region. Let's say I have a shared memory region which is used by which is actually having a data collection for your system performance. Okay, so that if a process maps to that segment, that shared segment, it will come and map here in this process address space, right? So this is actually logical addressing. I'm telling you, this is actually a logical addressing, that process sees to itself from 0 to f, right? But in between, when it goes to the RAM, it is a bit different, this story. We'll look at it. Okay, so we'll do it here. Okay, so this is your process address space. Okay, now what I am trying to tell you is, let's say it starts from 0 from here to ffff, and every page means, let's say we have page size of 4K. So 4K means you have 12 bytes reserved for your offset in a page. Okay, now you are left with 20 bytes. So 20 bytes will have that depends on the architecture, how many bytes we will use it for the page mapping. And then okay, we will come to that address translation on the virtual memory class. We'll try to understand what is process address space right now. So process address space is 0 to ffffff is the last location of your process. So it will start from 0 here, then every byte is like 0000001, so something like that. So it will every block, every one byte is addressable by 32-bit pointer, is 2 to the power 32 bit of space. So 2 to the power 32 bit is the 4 GB of space. So it so your addressing of your process is from 0 to 8 times f here, right? The last byte. This is, let's say this is your first byte, and this one would be your last byte. So uh, look at this one. Where is that process address space? So memory map region is, so every block, every section of that process address space is defined to keep some data, right? So you can see this area, right? From 0804800, from this area 0 to this area is actually unused. So this, you can say, a kind of padding which is being used by kernel. Why it do so? There is a reason behind it, because sometimes you may have to exec the process. So executing, do you know executing? What is executing?
It is something like it replaces the process space.
Yeah, so basically replacing the text segment of the process, right?
Yeah.
Yeah, so it's a loader call. So you can see why we keep it unused spaces. Sometimes
One
you
question:
yeah
It's only replaces that segment. What will happen to the stack? for example, if someone called two three functions and then later they are calling exec,
Yeah, yeah. So,
then
so it
will
will,
the stack,
yeah,
yeah, will,
everything will be wiped out. So that stack frame is not valid at all.
yeah, yeah, okay,
Yeah. So this is a very critical part of process management. Basically, what does happen when fork is called, and what does happen when exec is called. So basically, your whole Unix system is running on two things. Uh, one is your fork, creating new processes, and then executing it. That means creating making those processes live with changing the text segment of that. So every time you run any command in the shell, basically shell forks itself. So another process is created of type shell, then that shell actually finds out that binary. So ls command binary, it will found in, let's say, slash bin slash ls, so it will exec it. So you must look into one of the projects we did in nectech sometimes back, as a it was an educational project. uh, I'll show you one of the projects here. uh, nectech linux shell. Okay, it's a very simple shell written by us long back. So look into the input parser. So input parser is basically whenever you pass ls, so ls and space hyphen l. So how does it handles that input string, right? So input parser will have that kind of logic here. You could be able to see here. uh, okay, change directory is a special case. It's a shell internal command. It doesn't fork and exec. Okay, so there are a lot more changes we did into this. You can look into where is that source code. um, Not an input parser. I need to go into command execution, right? So here you can see fork and exec, the bottom. So see, it's a very simple. This function call happens when it does all the input parser thing and everything. So it actually passes us what command user has given to us. Okay, and it actually forks the shell process. Its own kind of process. You can see it here. It forks the process, and then it exec it here. You can see that this exec p, right? So basically what how the shell functions is basically every time it fork and exec. And this is one of the good, I would say, it's quite basic and very
can you share that link?
yeah, I'm sharing it to you. Just review the code. You will find it very interesting how actually it's a very minimal shell. Okay, quite very minimal shell. You can have a look into the source code. It clarifies lot of system internals, you know uh, things, how it is happening inside system. So uh, that I have already kept in. Okay, let me put it here and chat window also. I think G2 also has written code here in Nectar Clinic shell. I guess so. Yeah, he did that. It was part of his third year project, third year industrial project. So Where how to go into the change log, a pull request. Okay, yeah, he did that contribution to this. So look at this one. uh, what was the contribution to Linux shell? Okay, so you can have a look, you can have a look to this source code. This is very basic and very important one, I would say. You can have a look into Nectec Linux shell source code, and um, you would it will be really good to have this. So you can even install it in your Linux box. You can find the steps to do it. So you need to download. Please run following commands on the Linux terminal. You need to clone this um, repo, git clone command, then get into the directory and run these three commands. Then Nectec shell will be up. So it's a quite very minimal shell. You can run quit or q to exit from the shell. So you can also debug it. You can compile it with the debug option, and you can debug it also. So that will give you a very good flow. Yeah, very, you would be able to understand very good flow of that. So next the next thing I planned to cover today was uh, telling you about. Okay, so process address space. So we reached till memory mapped region. Basically there are shared memories which need to be mapped, and after that there is a memory range which is used for your heap and stack. So stack and heap is basically runtime data which is generated by function calls, and basically also dependent on um, how much memory is being allocated from user. So uh, okay, so here this is the process address space, basically a generic one. I am also putting this particular link for your read. So all right.
Can you elaborate that memory mapping means what? That shared library?
Okay, so memory mapped and shared libraries are you um, you take an example of a library, let's say stdlib, right? Stdlib is a library. So basically your different processes are using it, right? So what we do basically in that sense, in that situation when you have shared library concept. So libraries are basically two things. It has text which is used by all the process. Text means your execution statements, your functions which is exposed by library, that we call it text. And another thing is the data which is local to every process, right? So this the way of doing things effectively is to have that memory region placed in your memory at one place, and rest and allow rest of the process to map that segment if they are using that library. So let's say my five process are using this. So I'll show you pictorially how it actually looks like let's take an example. It's stdlib. Okay, this is your shared segment. Now what could be the effective way of dealing with it is, okay, so I have these three process. Okay, basically you can see that these three process have, okay, these three process have stdlib object, right? Stdlib is a library which is being used by all these three process p1, p2 and p3. Now basically in your memory architecture, in your whole memory, this stdlib segment is actually placed in one place, but that address is mapped by each of the process. So it is called memory mapped, that you have mapped that memory region into a logical process address space. So I mean, uh, yeah,
Mapped means it's not having a pointer, right?
mapped means okay. I'll take you this one. Okay, this is your physical memory.
Okay.
Okay, physical memory, and you have inside physical memory you have kept stdlib here. Okay, now what is addressing of a process is, process will always keep this shared library into this segment, right? From this address space, from this address to this address. But this physical memory addressing scheme is different. So what memory map means is that this particular the address translation always have this memory mapped to this address space, this address of the your process address space. That is called memory mapping. Okay, because this text is going to be same across the processes, right? Now your physical memory do not need to keep multiple copy of stdlib,
Okay.
right? If the physical memory will have just one copy of stdlib, it is mapped to the process address space,
Okay.
right?
This look like a even device mapping also will have, right? Memory
Yeah,
mapped device.
yeah. So I mean the concept in kernel is almost same everywhere. It is applied in a different so whenever people come to a problem where we are going to deal with the common data, right? And common data means you take example of fork also. So whenever you fork a process, the new task structure is created. Actually process is not being copied,
Hmm.
right? So your all everything is same. It will be assigning new places, new addresses in physical memory, depending on if it keep on changing the pages in the process address space. So let's say it call exec, then only it will find new place in physical memory. So in between that, basically this virtual memory comes into the picture, which I am not trying to touch right now. That's why I am trying to explain you in this way.
Okay.
So virtual memory session will clarify a lot of doubts in your addressing and capability scheme. Chetan, I have to I'm so sorry for this interruption basically, but we don't have power since morning in our apartments. And
Okay.
I was presenting this session on the laptop battery, and unfortunately it is getting down. You can see it's 6%.
Yeah. Right.
Yeah.
Yeah.
So what I am not finding any clue that whether it is going, the power will be here or not in some time. If it doesn't happen, let's wipe it out. I will cover the next session, because there is no power. It's pointless of, I couldn't help it at all. Right.
Yeah.
So I'm sending you these two things, right? You can, okay, it is very important one, man. Okay. Okay, I will give you one pointer which you can try it on. Instead of going into all these things, right? I will ask you to do one thing. Go into the task structure. Okay,
Okay.
task underscore struct. So you can find it there. If you go into the kernel source code, right? Scat.h, there is a file. So you can start cscope and you can see scat.h, right?
Okay.
Scat.h, it will be in kernel scat.h. User include, okay, you can find it there also. Either here you can find task struct.
Okay.
It's too much. Okay, I will tell you the better way of searching it. So in C programming, there will be, you can find lot of it. It searches for a lot of pattern. So you do this task underscore struct. You can do a pattern search here and give this will take you to the definition, because it must be having the open braces, right? Wherever
Okay.
the so this is like a cheat code, I mean,
Yeah.
to reach to the file, because a lot of files we don't want to search it everywhere, right? So you can go to that file scat.h, scat.h task structure. Read about each field. There is a description of each field. Okay, you will find open files. So file descriptors, there is a description how, why it is there in the task struct. So go into that. Okay, so this scat.h is in include linux scat.h. Okay, the location is include linux scat.h. this is the this is the file. I'm copying this. Okay, it is telling me that it is low. Anyways, I'll let me complete it. So yeah, right. Let me send you the mail also. Yeah. So you can find it there. Read the task structure. It has something like, you can see, um, like ft. Where is ft? There are file descriptors. File descriptor table is there. You can read each of the entries, what it is meant for, or how you can find the child of this process, how you can find the parent of this process. So just look at the this all fields. It is very it will look very vague right now, but I will connect the dots how you can use these fields in handling and managing the processes from your drivers and maybe a character driver. And do one more exercise that will be good for your understanding, that whenever you try to read and write to your character driver, right,
Yeah.
you see things in the message, right? So
Okay.
what you need to do, you need to also print your, let's say you are doing cat to that, your character driver, right? You are usually
Yeah.
doing echo and cat. Reading you do cat, and for writing it to you do echo, right? So whenever you read or write to it, it should also print the process id and the process name,
Okay.
right? So try doing that in your driver. That would be a good exercise to use the task structure in a way, how to use task structure in your way. And I will give you the solution of that when we will meet next Saturday. Today's session was, unfortunately, we have to stop it in between. Okay. Yeah.
Okay.
So Chetan, I'm it's 2% now. I'm stopping now and taking off here right now. We'll
Okay.
cover things next session. Okay.
Okay.
Yeah.
Okay. Thanks.
Okay. Thanks, Chetan. Yeah. Bye bye.